Good morning, I'm Mrs. Michak, and today we're going to be doing a couple of practice problems. So our first practice problem says calculate the temperature of 2 moles of a gas occupying a volume of 5 liters at 2.46 atmospheres. So we don't know what type of problem this is. So we're going to write down all of the variables that we are either asked for or are given in this problem. So we are given, or we are asked for temperature, so temperature equals, I'm going to say question mark, 2 moles of gas. Remember, moles are represented by N. And volume is 5.0 liters. And we have 2.46 atmospheres, ATM, and that would be representing a pressure. So as I look at this, I'm given 1 pressure, 1 volume, and 1 temperature. So that is a big indication to me that I have an ideal gas law problem. The ideal gas law is PV equals nRT. If you don't remember that, it is in your reference packet on page 3, PV equals nRT. And you might be wondering, hey, I'm missing R. Well, R is also in your reference packet. It's on page 1. So you can look up and find which R we're going to use. Right here, we're going to use the top one, 0.0821 liters times atmospheres times moles, or divided by moles times Kelvin. Why are we going to be using that one? So our pressure is in atmospheres. All right. In order to solve this problem, we need to get temperature by itself. So I need to divide both sides by nR. So now I'm going to have temperature is equal to PV over nR. And now I can start to plug in all of the variables that I have. So P is 2.46 atmospheres. V is 5.0 liters. N is 2.0 moles times R. Remember, R is a constant. So as long as as long as our pressure unit is in atmospheres, our R value will be the same, 0.0821. And yes, you do need to include this unit. You'll see why in just a second. Liters times atmospheres divided by moles times Kelvin. All right, before we multiply all of this out, I want to make sure that our units cancel to the unit that we need to be left with. So we are looking for a temperature. So the temperature in gas laws is Kelvin. So I want to make sure that we're actually going to be left with Kelvin and that we've done the problem correctly. This is an easy way to check to make sure that all of your units or all of your numbers are in the right place. So atmospheres are on the top of our mathematical expression, and then over here they are on the bottom, and you'll notice that this is another division, but it's on the top of that, so that cancels. Same thing with liters. And then we have moles. Moles are on the bottom, but then they cancel with this one where moles are on the bottom. Okay, so we have moles divided by moles. So we're good there. Then we have Kelvin. You might be like, Kelvin's kind of in a weird position where let's forget about all our numbers for just a second. Just pretend like they're not there. And we've canceled all of our other units. So let's look at Kelvin. We forget about our numbers, then we'll be left with this. So all of our units cancel. Would this be Kelvin? Okay. Well, let me ask you this question. If I have 1 divided by 1/2, what would that equal? Well, that would equal 2. If I have 1 divided by 1/3, what does that equal? Well, that's 3. And I can keep going. 1 divided by 1/4 equals 4. So yes, 1 divided by 1 divided by Kelvin does equal Kelvin. So Kelvin being located right here will ultimately cancel out to give me a Kelvin unit. When you go to plug all of this into your calculator, make sure that you put parentheses around everything so that your calculator performs this mathematical expression correctly. Either that or multiply your 2.46 times 5, hit enter, then separately do 2 multiplied by 0.821, then divide the number that you got for this by this and hit equals. Okay, so the way that I do that is I actually do 2.46 times 5, I hit enter, then divided by, and then I put a parenthesis around this, 2.0 multiplied by 0.0821, unparenthesis, equals, and I get 74.908, which I'll round to 74.91. Alright, and if you felt pretty good about that problem, you can read the next problem and go ahead and do it by yourself, fast forward and see if you get it right. If you did not feel so great about this problem or you were kind of confused, then I would follow me through the next problem. Alright, so the next problem says to calculate the mass of nitrogen gas that occupies 3.45 liters at a pressure of 150 kPa and a temperature of 45.6 Celsius. So just like the last problem, I'm going to write down everything that I have or that I'm asked for. So it asked me for mass. So I'm going to write mass equals that occupies 3.45 liters. Liters is volume. Pressure, 150 kPa. And a temperature of 45.6 degrees Celsius. Alright, so let's look at our reference packets. On page 3, and you might notice that there are no problems or no equations that involve mass, volume, pressure, and temperature. The closest that we have is, again, PV equals nRT. Because we can look up R, so then we'll have pressure, volume, the R value, and temperature. We would be able to solve for N, which is the number of moles. So again, using what we have, we can decide on the value for R, and using kPa, you can look up the value of R, would be 8.314 liters times kPa, divided by moles times Kelvin. That's on the front of your reference packet on page 1. And then I'm able to solve for N. So you might be going, okay, well, why am I going to solve for N, which is the number of moles, if I'm looking for mass? Well, remember from the beginning of this year, or close to the beginning of this year, we're able to convert from moles to mass. Remember mole time. It's a fun place. Okay. I need to do before I actually start this problem. First, I can't use this temperature. You'll notice that my R value has a K in it for Kelvin. This temperature is in Celsius. So I need to convert it to Kelvin by adding 273. And that is going to get me 45.6 plus 273 equals 318.6 Kelvin. And I believe that now I'm ready to go. So again, similar to the last problem, I'm going to rearrange my formula so that I have N by itself. In order to do that, I'm going to divide both sides by RT. So now I have N is equal to PV over RT. So N is equal to P, 150 kPa, times my volume is 3.45. Divided by my R value is 8.314. And remember, you do need to include this entire unit. Liters times kPa this time over moles times Kelvin multiplied by my temperature is, make sure you use the Kelvin value so we can cancel our units. If we use the Celsius value, our units would not cancel. Alright, just like last time, I want to make sure all my units cancel and I'll be left with the proper unit. So kPa cancels, liters cancel, Kelvin cancels, I'll be left with moles. N is the number of moles, so I'm good to go on that front. And also, make sure that you are putting parentheses around things or hitting equals between when you do these, so that you are performing this mathematical expression correctly. So 150 times 3.45 divided by 8.3 multiplied by 318.6, and I get 0.195 moles. But again, back to the beginning of this question. It does not ask me for the number of moles. It asks me for the mass of specifically nitrogen gas. Well, nitrogen gas is one of our diatomics, so it's actually N2. So I have 1.95 moles of N2. So I need to convert that to mass. I'm going to put this over 1. That 1 is just a placeholder. I have 2 nitrogen atoms for every 1 molecule of nitrogen. So I multiply by the molar mass of a nitrogen atom. I get, and this from the periodic table, so I get 28.02 grams per mole. What does that grams per mole mean? Well, it means for every 1 mole of nitrogen molecules, they are going to have a mass of 28.02. So then I'm going to use this. I'm going to plug into my conversion. This 1 mole of N2 is going to go on the bottom. Why does it go on the bottom? So my units cancel. Moles of N2 cancels with moles of N2. My 28.02 grams of N2 will be on the top. Since that doesn't cancel with anything, that's going to be the units that I'm left with. So I'm going to take my 0.195 multiplied by 28.02, and I get 5.47 grams. nitrogen gas. So, that's not quite everything that I can ask you about the ideal gas law. We did a problem where we calculated temperature. We did a problem where we used the number of moles to calculate the mass. Probably not going to have you calculate the ideal gas constant since they're given in your reference packet. But I could also have you calculate pressure or volume, or going back to the number of moles, I could also have you calculate the number of particles using Avogadro's number, 6.02 times 10 to the 23rd particles in 1 mole. So keep in mind those things as we are moving forward and as you're doing practice problems in your homework. And that's the ideal gas law.